the data came back wrong. Not slightly wrong, not off by a small margin, wrong in a way that forced astronomers to stop, step back, and quietly question everything they thought they understood about the origin of the universe. In the first 18 months of full operation, the James Webb Space Telescope sent back images of galaxies that should not exist. They were massive, fully structured. Some of them had already lived through multiple generations of star formation and death. And according to every calculation, every model, every equation that modern cosmology rests upon, they had done all of that before the universe was even old enough to allow it. One galaxy in particular stopped researchers cold. It carries the designation JADES GS 140. It sits at a redshift that places its light more than 13.4 billion years in the past, and it is not a whisper of a young cosmic structure. It is enormous, bright, chemically complex, a finished galaxy in an era when the universe had barely switched on its first stars. That contradiction is not a data glitch, it is a signal. And what it points to may force the rewriting of the most fundamental story humanity has ever told about itself, the story of how everything began. To understand why Webb's images are so destabilizing, you need to first understand what scientists expected to find. The standard cosmological model, known as lambda CDM, has governed astrophysics for decades. It describes a universe born approximately 13.8 billion years ago from an inconceivably hot and dense singularity, a point smaller than an atom, containing all the matter, energy, and space-time that would ever exist. Then, in a fraction of a second, it expanded, not like an explosion in space, like an expansion of space itself. In the first 3 minutes, the fundamental particles fused into light nuclei, hydrogen, helium, trace amounts of lithium. For the next 380,000 years, the universe was a dense, glowing fog, opaque and featureless. Then, as it cooled, electrons slowed enough to be captured by nuclei. Atoms formed for the first time. The fog cleared. Light traveled freely across the cosmos for the first time in history. That ancient light still reaches us today as the cosmic microwave background, a faint cold hiss of radiation that has been traveling for nearly 13.8 billion years. What came after was a long silence. Known as the Cosmic Dark Ages, this era lasted roughly 200 million years. No stars, no galaxies, just vast clouds of hydrogen and helium drifting apart in the expanding dark, slowly beginning to feel the pull of gravity. Over millions of years, pockets of gas collapsed under their own weight, grew dense enough to ignite nuclear fusion, and the first stars were born. Small, hot, impossibly bright. Those first stars exploded quickly, seeding the universe with the heavier elements that would go on to build everything else. Carbon, oxygen, iron, the raw materials of planets and life. According to the model, galaxies, real structured massive galaxies, should not have appeared until well over 1 billion years after the Big Bang. Building one takes time. You need generations of stars to form and die, to synthesize heavy elements through nuclear burning, to scatter those elements across space through supernova explosions, to allow new stars to form from the enriched debris. The process is slow, hierarchical, bottom-up. Smaller structures form first, then they merge, then they build. Then, slowly, a galaxy takes shape. That is the timeline, that is the model. That is what every telescope before Webb confirmed. Then Webb looked, and the timeline broke. The James Webb Space Telescope is, in every practical sense, a machine built to see the past. Light travels at approximately 300,000 kilometers per second, fast but not instantaneous. When you look at a star 100 light years away, you are seeing light that left it 100 years ago. The star you are observing may not even exist anymore. The farther you look into space, the farther back in time you see. Webb's design was built around this principle. Its primary mirror, a honeycomb of 18 gold-coated beryllium segments spanning 6.5 meters, collects more than 6 times the light-gathering power of the Hubble Space Telescope. It sits 1.5 million kilometers from Earth, parked at a gravitational balance point called L2, shielded from the sun's heat by a sun shield the size of a tennis court. Its instruments operate at temperatures near absolute zero, below minus 230 degrees Celsius, cold enough to detect the faint infrared glow of the earliest objects in the universe. Infrared light is essential. The universe is expanding. As light travels across billions of light years, that expansion stretches the wavelengths, shifting visible light into infrared frequencies. The more distant the source, the greater the redshift. A galaxy from the universe's first few 100 million years would appear completely invisible to an optical telescope. To Webb, it glows. So astronomers pointed it at the sky and they waited. The first anomalies came quickly. In a patch of sky smaller than a grain of sand held at arm's length, Webb resolved dozens of candidate galaxies sitting at redshifts that placed them within the universe's first 700 million years. That alone was remarkable. But when researchers measured the masses, the brightness, and the structural complexity of these objects, something became deeply uncomfortable. The galaxies were too big, not slightly above expectations. In some cases, hundreds of times more massive than any structure that should have had time to form. One study, published in the journal Nature Astronomy, described the discovery of 6 massive galaxy candidates dating to just 500 to 700 million years after the Big Bang. The researchers calculated that the stellar mass contained within these structures would require an efficiency of star formation approaching 100%, meaning nearly every atom of available gas would have had to be converted into stars with almost no waste, no turbulence, no delays. That is not how star formation works. In today's universe, only a fraction of available gas becomes stars. The rest is blown away by radiation, pressure, stellar winds, and the explosive deaths of massive suns. The efficiency of the process in our own galaxy is perhaps a few percent at most. To build these observed structures in the available time, the early universe would have had to behave in ways that have no analog in any era we can observe. Either physics was fundamentally different in those first hundreds of millions of years, or the universe had far more time to work with than the standard model allows. There is a third possibility, one that most cosmologists are reluctant to say out loud. Maybe the Big Bang was not the beginning. That statement needs to be handled carefully. No serious physicist is claiming that nothing happened 13.8 billion years ago. The evidence for a hot, dense early state, the cosmic microwave background, the abundance of light elements, the large-scale structure of the universe is overwhelming. Something occurred, something vast and violent and foundational. But whether that event was an absolute beginning, a moment before which there was literally nothing, no time, no space, no physics, is a question that sits at the edge of what science can currently answer, and Webb's anomalies are pushing it closer to the center of the conversation. The first theoretical response has been to revisit the early universe's physics. Some researchers suggest that dark matter, the invisible substance that accounts for roughly 27% of the universe's total mass energy, may have behaved differently in the earliest epochs. A faster than expected clumping of dark matter could have created the gravitational scaffolding for galaxies to form earlier and more efficiently than standard models predict. This is not a radical departure. It works within the existing framework, but it requires calibrating the model with parameters we do not yet fully understand. A more provocative hypothesis involves the nature of cosmic inflation itself. Inflation is the theory that the universe underwent a period of extraordinary exponential expansion in the first tiny fraction of a second after the Big Bang. This expansion is invoked to explain the uniformity of the cosmic microwave background. The fact that regions of the sky that were never in causal contact with each other have identical temperatures. But inflation's details remain contested. Different inflationary models predict different patterns of early structure formation. If inflation was more complex, or more prolonged, or more uneven than standard versions assume, the seeds of early galaxy formation could have been laid down much earlier, and on larger scales than current models allow. Then there are the cyclic cosmologies, theories in which the Big Bang was not a beginning but a transition, a bounce from a previous contracting phase, or a collision between higher dimensional membranes in a framework inspired by string theory. In these models, what we call the Big Bang is simply one event in a much longer cosmic history. The universe that existed before that event would have left no direct observable trace, except, perhaps, in the form of structures that seem too old, too developed, too advanced for the age we assign to them. This is where Webb's images become genuinely unsettling. Not because they prove any of these alternatives, they do not, but because they introduce enough tension into the standard model to make these alternatives newly serious. An anomaly that can be explained away is anomaly, an anomaly that persists across dozens of confirmed observations, across multiple independent research teams, across multiple instruments and methodologies. That is a crack, and cracks in science have a way of growing. The universe is not required to be what we expect. It was here long before we were, and it has been operating by its own rules since before the first light. Here's where the story stands today. The anomalous galaxies are real. The measurements have been confirmed by multiple teams using independent technique. The most distant confirmed galaxy, Jade's GS 14-0, has been verified spectroscopically, meaning its redshift, and therefore its age, is not a photometric estimate, but a direct measurement of the light itself. It exists. It is old, and it should not be possible within the timeline we have been working with. No one has a clean explanation. Some astronomers remain confident that refinements to the standard model will eventually resolve the tension. New data on early star formation efficiency, better constraints on dark matter clustering, improved simulations of the first billion years, all of these could bring theory back into alignment with observation. Science has done this before. An anomaly appears, the model is adjusted, and the anomaly is absorbed. But others are less certain, because the anomalies are not isolated. They accumulate. Every new deep field image Webb returns seems to add another galaxy that arrived too early to the party. The tension does not seem to be softening. It seems to be sharpening, and the sharpening points to a possibility that is simple in its statement but staggering in its implications. The universe we can see may be only a chapter in a story that began long before the Big Bang. What came before, whether it was a previous universe, a higher dimensional collision, a cycle without beginning or end, is not yet within our reach. But Webb is moving the boundary of what we can ask. Every image it sends back is a question addressed to a cosmos that has, until now, kept its oldest secrets in the dark. The question is whether we are ready for the answer. If the cosmos has been speaking in signals we were not designed to hear, then every new instrument we build is an act of translation, and some translations, once understood, cannot be forgotten. Subscribe, because whatever Webb finds next, you should not miss it.